Now, the high heat index values do have consequence, and so it's important to understand this feature as well. The higher frequency of heat waves in our region has led to a number of other changes. We now measure different seasonal dynamics of plant pathogens, parasites, insects, and microorganism populations that fundamentally love tropical-like weather, and therefore they do very well when we have these spells of high dew point and high heat index conditions. We've also had a public health concern for this in that we have segments of our population, those with multiple sclerosis, chronic obstructive pulmonary disorder, and other maladies, are hypersensitive to when we have tropical-like air masses and dew points above 70, and especially heat index values above 100. And so overall, there's been a net change in the caregiver community to gear up for this and better care for these people. We've also realized livestock loss, according to those that work in the livestock areas in our region. We've had spells where we've lost a lot of birds with heat stress, particularly in the turkey industry. In the dairy industry, we've lost a lot of pregnant cows due to abortions brought on by the heat stress under these conditions. And lastly, from an energy standpoint, we've become quite sensitive to having air conditioning and controlled environments available to us to escape the heat stress. And so if you look now at all new construction standards, and you even look at retrofits or renovations in the northern Minnesota climates that formerly needed no air conditioning, you will find that air conditioning is mandatory in those environments to escape these spells. The third feature of the regional climate changing quite distinctly is precipitation. This is a graphic of the statewide precipitation pattern in Minnesota going from the late 19th century to the current. It's a compilation of well over 1,500 precipitation observers on the landscape measuring daily precipitation. We can see the trend in recent decades is upward. We can also note that the wettest year in Minnesota history was in 2010. That's illustrated in this. We can also see the waxing and waning across time of the precipitation environment on our Minnesota landscape. Back in 1891 to 1920, the region of the state in the light blue and dark blue illustrated on this slide received over 29 inches of average annual precipitation. By the time we got into the mid-20th century, we see that the area of 29 inches or greater contracted to the southeasternmost counties. Then later in the 20th century, it began to expand again, and now in the modern era, illustrated over here, we see that well over half the state landscape calls 29 inches or greater normal annual precipitation. Seasonality in this climate parameter, this moisture parameter, is not as distinct as the temperature seasonality is, but you can see, for example, winters have dominantly been wetter than normal in recent decades. Springs, too, have been dominantly wetter than normal. Autumns have been wetter than normal, and summers have been mixed, both wet and dry. Some of the background normal or frame of reference, location by location in our western Great Lakes region has changed. This is an example from a southern Minnesota location, which once had an average annual precipitation about 27.5 inches, and now it's well over 35.5 inches is what we call normal in that particular region. We can look at another spot on the landscape in central Minnesota and see that at Willmar, for example, we once called 23 inches normal there, but we now are almost 29.5 inches in terms of what's normal in that part of the state. Embedded in these quantity shifts in precipitation change are some character shifts, illustrated in a recent research by the Intergovernmental Panel on Climate Change, which in the lower map on this slide simply shows you the global landscapes, many of them embedded with a plus blue sign to say that precipitation has not only changed upward or become a larger value in those landscapes, but that there's a greater contribution from convective thunderstorm precipitation, the kind of precipitation that delivers a lot of rain in a short period of time. That's why we have to give more attention to the precipitation climate attribute, more attention to it than simply measuring its quantity, because we need to note how its type has changed, whether it's liquid or frozen. We need to know how the intensity has changed, how much comes how fast, how its frequency has changed, how often it comes, with what duration, and if there have been any seasonality shifts. All of these are important because they play out consequentially on the landscape. One area where they play out is in the incidence of flash floods. Now, in the Western Great Lakes region, where we've dissected the history of flash floods across the landscape, we find that flash floods are occurring with greater frequency. We can further break this down by looking at the frequency distribution of, say, 3, 4, 5, 6-inch thunderstorm rains. This graphic illustrates the frequency of 3-inch thunderstorm rains in our region and simply shows that this frequency has been increasing. The new statistics derived from the National Oceanic and Atmospheric Administration, where we've incorporated all the more recent decades of data, show that there's been change in the 5-minute maximum value of rainfall, the 1-hour maximum value of rainfall, the 1-day maximum value of rainfall. And now all of these new statistics are available online in a product called NOAA Atlas 14. And so if you Google that term, you can go to it, find it, and you can look at any point on the landscape and find the newly derived values for precipitation, intensity, frequency, most of which show significant change. Hand in glove with the change in the character of precipitation, that is, being more dominated by convective thunderstorm activity, we must also acknowledge that convective thunderstorms are about who gets it and who doesn't, where it falls and where it doesn't. There's magnified geographic disparity with thunderstorms. We all know that. Some areas get 3-4-inch rains while other areas get entirely missed. As a result of that character change, another feature of the Western Great Lakes region landscape we're noticing is that drought, especially severe to extreme drought, is showing up somewhere on the Western Great Lakes landscape with greater frequency. In other words, areas are getting missed with the thunderstorm rainfalls. And you can see from this list of all drought years in the region that since the new millennium, since the year 2000, we have had more years with drought present on the landscape than without. Also embedded in that signal, if we look at the attributes of what we call severe convective thunderstorm development, we look at the measured attributes of the atmosphere, such as the lapse rate or change in temperature with elevation. We look at the wind shear aloft, the change in wind direction and speed as you go up through the vertical atmosphere. We look at the mixing ratio. We look at the amount of water vapor in the atmosphere. And what's been done recently by Dr. Harold Brooks at the Severe Storms Lab in Oklahoma is he's found that these so-called severe weather attributes of the upper atmosphere are migrating to higher latitude. Simply stated and shown on this map is that over North America, the common convective thunderstorm attributes that were more frequently measured over the lower plain states like Texas, Oklahoma, and Kansas are migrating to higher latitude and are now measured with greater frequency over states like Iowa and Minnesota and the Dakotas and even the Canadian provinces like Manitoba and Ontario. As a result, this is playing out with more powerful convective thunderstorms over these landscapes. And for example, the Minnesota State Climate Office, illustrated in this sequence of 3 maps, has documented that in southeastern Minnesota counties, all illustrated in these maps, we have had 3 1,000-year rainstorms since 2004. These are the 8, 9, 10, 12, 14-inch rainstorms that tend to massively flood the landscape, all the watersheds associated, as well as the structured landscape, the properties, the homes, the bridges, etc.